0, base 16. That's the lower region. The upper region goes to 0 again, and then we have F, F, and F, base 16. The next region, again, this is 0, 0, 0, and we have the value here in binary 1, 0, 1. So we have 1, 0, 0, 0, so 1, 0, 0, 0, base 16, up to the value again of 1 and all ones, F, 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 base 16. So that's the second region. That's this region here. This region, well, we have 0, 1, and so that has the value of 2. So the next region, 2, and then followed by 3 zeros, base 16, up to the value of 2 and 3 Fs. And finally 1, 1, that's 3. And all zeros, base 16, up to the value of 3 with 3 Fs. So these are us breaking up our address blocks, and we're defining the lower and upper bound addresses in hexadecimal. The next thing we want to do is generate the decoders based on these values, i.e. bits A13 and 12. So we have bit A13, A12, and we have 1, 1, 1, 0, 0, 1, and 0, 0. Okay, so in this region where A13 is 0, 0, and then we have this region where we have 0, 1, then 1, 0, then 1, 1. Now, normally our address bits are assertive high, and let's have our memory chips that we're going to be using also assertive high. So to activate them we need a high output, and the inputs are going to be assertive high. For the lower region, i.e. where A13 has the value of 0 and A12 has the value of 0, well, if I use a NAND gate, if A13 is assertive low, assertive high, and A12 is assertive high, we're going to create mismatches, and so when we have the value of 0, 0, this is going to become 1, this is going to become 1, and the output will be 1. And so this will activate our output here. Let's say O for output, assertive high, and this will be mapped onto our first block, the lower block, i.e. for the address range of 0 to 0FFF base 16. Moving on to where A13 has the value of 0 and A12 the value of 1. Well, again, let's use the same assertions, i.e. the address bits are assertive high and the memory chip that we want to activate is assertive high, and so we will use again a NAND gate. Now A12 itself will be, we want it to have the value of 1, so what I will use is effectively an inverter with the use of a NAND. So we have A13, A12. Now A12 here is assertive high, A13 is assertive high, this A12 is assertive low by the use of an inverter, and this will activate the chip. And so this is the second region, let's call it 1, and again it's assertive high, and so the address range for this will be, as we defined it, 1000 base 16 up to 1FFF base 16. The next we have where A13 and A12, that has the value of 10, so it's effectively the opposite circuit in terms of the inputs. So we have a NAND gate, and we have A12 feeding directly as assertive high into our gate. A13 assertive high. So if I draw an AND gate here, so in this case where this has the value of a high and this has the value of 0, that will yield then this as a value of a high. And so our address range as defined as before, that is 2000 base 16 up to 2FFF base 16. Finally, the upper quarter region where A13 and A12 both have the value of 1. Well, here we need two inverters. So A13 assertive high, A12 assertive high. This is A13 assertive low, A13 12 assertive low, and the output there. Let's label this 3 assertive high, and the address range for this is 3000 base 16 up to 3FFF base 16. So that's it.